Hey there, this is Math 7, Unit 7, Lesson 7, Building Polygons Part 2. We're going to be building more triangles today. And first of all, this is a little story about Lynn. It says, at a park, the slide is 5 meters east of the swings. Lynn is standing 3 meters away from the slide. How far away from the swings is Lynn? And draw a diagram. Okay, so let's just draw a diagram first of all. I'm going to start here with a picture, just so I get a picture of what's going on here. So we know we're at a park and we have a slide. We have a slide of some sort, so we draw our little slide, however that you want to make that look. Alright, so here's our slide. Comes up there, we have the ladder to go up the slide, looks great. Okay, beautiful slide. So we have our slide, okay, and we know the slide is 5 meters east of the swings, so between here and the swings, and we can draw them like so. Okay, we have our swings. The distance from here to here is 5 meters from there to there. Lynn is staying 3 meters away from the slide. So Lynn is somewhere, and we could just make a point here. We could say 3 is like here, and we could draw Lynn right here at 3 meters away. Okay, and that's kind of the idea of what our picture looks like so far. Now, is this an accurate drawing? Not necessarily. So how far away is she from the swings is the question. What's the distance from here to here? Now, we can't answer that right away because here's the thing. We know that this is a set distance. We know that this to this has to stay 5 meters. But we know that her distance is 3 meters away from the slide. Not from anything else, but from the slide. That means she could be 3 meters this direction, and really, if we were to think about this here, she could be anywhere in a 3 meter radius of that slide. There's 3 meters here, be 3 meters there, 3 meters there. She can actually be anywhere on that circle. So for Lynn, how far away from the swing she is depends upon where she is in this 3 meter radius from the slide. If she's here, we know that it's going to be 5 meters minus the 3 meters to tell us that she's going to be 2 meters away. Right? If she was standing right there, that's 2 meters away. But if she's over here, then it's going to be 5 meters plus the 3 meters to tell us that she is 8 meters away. So there's a distant difference there for how far away Lynn could possibly be. Is there anywhere else she could be? Sure, she could be at any point along this circle, and that's where she could be because that would all be within 3 meters of the slide and would be just fine. Okay, so again, that's my picture version. If you were to use the applet that goes with the Desmos, again, the same idea is you take Lynn. Oh, come on, wake up, Pin. Okay, we take Lynn. Oh, we used the writing tool. I forgot. So let me get this back on. It fell asleep on me. Dun, 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 back on. I think we're good. Okay, so I come over here, I get the pin. And the idea is we say, here's our swings, here's our slide, and so Lynn is going to be anywhere in that circle region there, right? So that's the same picture, just with a little nicer slide and a little nicer set of swings. Isn't that sweet? Okay, let's look at the next thing. How long is our third side? Your teacher's going to give you some strips of different lengths and fasteners that you can use to attach the corners. Build as many different triangles as you can that have one side length of 5 inches and one of 4 inches. And record the lengths of the triangles that you build. Okay, so here's the idea. We're sitting here with a piece of paper. Okay, we have our triangles of lengths 5 and 4. Right, and those become 2 of our side lengths here, and then you have a bunch of other pieces of paper that your teacher gives you. Right, so they gave you a strip that was 3. Now because I'm using some thicker strips, I'm going to be looking at the inside lines. Okay, match the corners up and make the insides. Can I make one with 3? Can I get my corners to touch with 3? Looking here, yep, I can do a 3 and a 4 and a 5. I can get my corners to touch there, no problem. So 3 is going to work. That's a great one. When I look at my extra 4 that I was given, okay, put the corners there. Can I get these corners to touch over here? Play with it a little bit, and yep, I can do a 4. So 3 works, and a 4 works. Let's try a 5. Corner to corner, oops. Corner to corner for me, corner to corner for you, and I can do a 5. So a 5 works with my 3 and my 4. I can try a 6. And a 6, when I look here, what do I have? The 6 seems to work okay, so I get a 6, that's working. I'll try my 8 out right quick. And try the 8. Is the 8 going to work as well? It's going to be a little bit wider, that's for sure. But the 8 works, right? So all these links are working as an additional side link. So those work great. So indeed, I could say that the 3 works, the 4 works, the 5 works, the 6 and the 8 all seem to work. Are there other links that could be used to make this work as well? And that's a great question. There probably are other links that would work. Now what I set up real quick is I made a little diagram here with 0 to 9 on it, right? So if I took my 4 and I put it on the corner of the 5, I can try out some other measurements. So for example, I could look and see that, okay, I can get this to work a little bit, a little tricky there, but I can get it to work with the 1. All right, it's a little bit tough to do, but you get the idea. I can make it work with a 1, right? I can make a triangle space there. I could extend it like we already saw and get it out to the 2. I can extend it and make this angle down here a little wider and make it 3. I can get to the 4, 5. I can get to the 6. I can get out to the 7, no problem. We can stretch and make our way to the 8. Now to get to the 9, notice what happens when I get to the 9. What takes place? When I get to the 9, I can't quite make it to come together. In fact, when I do, now I'm back to a straight line. So, are there other line links we could have used? Sure. I can use anything between 1 and 8 are all going to be okay to use. Once I get to 9, it's not going to work anymore. Okay? So it's not going to work. And the 1 is a little tricky there too. So anything between 1 needs to be a little bit bigger than 1. Anything between 1 and 9 is going to work. So it has to be greater than 1, in this case here, and less than 9. Can't be exactly 9 or it's not going to quite work out. So the 1 doesn't quite work out for us either. It was a tough one to make work. So we would say that what else could use for sure? We could use a 2 and we could use a 7. Okay? Could be used. Are there any other links that were in your set but could not be used as a third side? We would say that the 9, which wasn't in my set here, but the 9 could not be used. It would just not work out for us. Okay? So that's kind of the idea with that activity did today. Assuming you had access to strips of any length and you use a 9-inch and a 5-inch strip as the first 2 sides, complete it. Complete the sentence. The third side can't be blank inches or longer. Okay. So how many inches or longer? So we're looking for the max it could be. The max it could be 9 plus 5 is 14. So it can't get up to 14 or longer. It has to be less than 14. And the shortest it could be, we would do 9 minus 5, which gets you to 4. So the third side can't be any shorter than 4 inches. All right, that's 4 inches or shorter. 4 inches won't work. It has to be a little bit bigger than that. 4.1 is okay. All right, so 4.1 is okay. Over here, 13.9 is okay. Just don't get that high. That's the idea there. Okay, let's take a look at the next activity. The next activity involves making some marks, swinging some stuff around, and we can use the applet for this again. Let me see if I can get this working for y'all, and wish me luck. Here we go. Get the right one. Huh. That's the right one. Okay. Alright, so here's our applet for this next one, if I got this right. I think I'm on the right one, pretty sure. Alright, so here we go. The idea with this activity is we're going to follow some instructions and see if we can do some stuff. We have a piece of paper that shows a 4-inch segment here, right? Oops, I don't know what that's doing. 4-inch segment, a 3-inch, and a 3" over here. First it says to put our 4" strip directly on top of the 4" segment, so we're there. Great. For now, ignore the 3", rotate it so it's out of the way. Rotate this so it's out of the way. Let's see. I think we're not quite doing our thing. My direction says, alright, let's do this part. 3, yep, swing around 3. Okay, so here's what we're gonna do. First thing says, if you want to make a triangle with side lengths of 3 units, 3 units, 4 units, how would you know what angle your position to be? Let segment AC be the 3rd side length, and then we're going to trace and drag. So what it wants us to do for now is we're going to click on this guy there, and when I hold it down, it gives me the option to show a trace, and I select that. Once I show trace, oops, I didn't quite click it there. I'll try it again. I show trace. No, try it again. Come on. Try my finger, and let's show trace. Okay, cool. When I show trace and I draw that 3 and make it go around, what do we notice? We notice that I am making a circle, right? And this circle has a radius of 3 as it goes around. No problem. Let's turn the trace off. Okay, so that's my 3 there. Now, that's the first step. Then after that, if we have that there, if we take the, okay, we're making a circle here, we know that we could use what's called a compass to make a circle like that if we chose to. And so if you have a compass in your geometry toolkit, you could actually put one point down on the A and then spread out to the 3 and draw that circle all around like that. Okay? Now, can we create 2 unique triangles now with a base of 4 and a side length of 3 inches? Okay, can we do that? And the answer to that would be sure, we certainly could do that, right? If I know that all I have to do is I know that my triangle, this one can be there, and whatever triangle I make, I could do a point from here to here, and I get a unique triangle like so. That becomes a triangle that I could make. All right, let me erase that line there. Oops. I could also, go back, and go forward, and go forward, and go forward. Nope, can't do that. Okay, so let's go back and do my trace again. Oh, arrow, sorry. I'm learning still. And show trace, and show trace. Okay, so now if I wanted to, if I put this arrow, this line over there, I could also make a triangle to go from here to here. So that's a different triangle than what I had a second ago, isn't it? Right? So I could put a triangle there to there. I could also, by moving this, you can see that there are several different triangles I could make with the same 3 inches here and 4 there. I can make that longer and wider to the point where it goes away and comes back this side, and these are also all acceptable triangles that I can make with the tool. So there's a large variety of triangles I can make with side lengths of 3 and 4, aren't there? Okay, so you can see some cool ways of doing that there. That's the idea. So we can take 2 side lengths, but if we only have 2 side lengths, there are still an infinite number of triangles we could make that would not be identical. Okay, so if I have a 3 and a 4, this length could be lots of other lengths. What I haven't established is what that angle measurement right here is going to be. Okay, and so we can see if I was to find the angle measurement for here to here to here. Whoops, let's try the inside. Dun, dun, dun. Oh no. Delete. No. Oh no. Good thing this is on video so you can all watch and go, oh my goodness, what are you doing? Alright, let's try the angle thing again. I'm going to go inside, inside, inside. Nope. I always had the worst luck with that. So it's going to be a difference there. So we have an angle measurement, there's the point, and we could continue and find other angle measurements. But as long as this is changing, then that's going to change as well. Okay, and that's somewhat the idea with that little activity. You'd probably do it with some paper and pencil. That's great. We just did the applet just for some fun there. So in summary, if we want to build a polygon with two side lengths given that share a vertex, we could think of this being connected by like a hinge that can be opened and closed, right? We get that nice little circle like so. All the possible positions of the endpoint of the moving side form a circle, which we showed with our example before, both with the slide story and then with the one we just did. You may have noticed that sometimes it's not possible to build a polygon given a set of lengths. For example, if we have one really long segment and a bunch of short ones, we can't connect them all up. Here's what happens if you try to make a triangle with side length 21, 4, and 2, right? No matter what I do, that side length won't connect to this one over here. It'll never reach, so we'll never have a triangle there. The short sides don't match up because they're too far away from each other, and that's kind of what happens. So if you draw that circle, you can see there's no way to make the endpoints ever get together. Okay, so in general, the longest side must be less than the sum of the two other sides. If not, you cannot make a triangle. Okay? All right. If we can make a triangle with three given side lengths, it turns out that the measures of the corresponding angles will always be the same. For example, if two triangles have side lengths of 3, 4, and 5, they have the same angle measurements. So if we have three given side lengths, then the angles will always be the same. So it won't matter. So if you tell me that it's that length, and that length, I drew that 100 times, I would have the same angle measurements every time I drew it. All right, let's take a look at today's homework. So press pause, do your homework, and let's come back and check it out. All right, number 1. In the diagram, the length of segment AB is 10 units, and the radius of the circle centered A is 4 units. So here to here is 4, which makes this distance right here 6. Okay, if the whole thing is 10, that gives me 6 there. Use this to create two unique triangles, each with a side length of 10 and a side length of 4. Okay, so I have to keep that 10 in place there, so I don't need this 4 and 6, that's fine. So I'm going to do a 4 out to here. All right, that's a 4. And I can make a triangle go out to here like so. That's one. I can also make one that goes like this, here to here, and then connect there to there. Right, so I could have a regular looking triangle or a very flattened one there. Two different triangles, no problem. Number 2. Select all sets of 3 side lengths that will make a triangle. All right, so 3 plus 4 is 7. Is 7 going to be okay? Remember, 7 has to be, when we add that up there, it needs to be greater than, so as I say, is 7 going to be greater than 8? 7 going to be greater than 8? Nope, it's not, so I would never connect. I'd have an 8 here, and a 3 and a 4, and they'd have a gap in the middle. So that would be a no. Alright, because 7 is not greater than 8. Here I have 7 plus 6 is 13. Is 13 going to be greater than 12? Yes, it will be. So we can connect them there, no problem. This next one, I take my two smallest lengths, 5 and 11 is 16. Is 16 greater than my largest length of 13? Yes, it is, so that would work. Here our smallest lengths are 10. Is 10 greater than 12? No, it's not, so that won't work. And here 4 and 6 is 10. Is 10 greater than 10? No, it's equal, which means it'll be on a line, but it won't make a triangle. So only B and C would work for us. Number 3, based on a signal strength, a person knows their lost phone is exactly 47 feet from the nearest cell tower. So let's call this our tower right here, okay? And we could draw out here to where the cell phone is going to be at 47 feet away from the tower. The person is currently standing 23 feet from the same cell tower, so maybe here at 23. What is the closest the phone could be? What's the furthest? Now again, if they're the cell tower 23, they're going to be in that 23-foot radius all the way around there, right? So in terms of the closest and nearest, it could be the whole 47 plus an additional 23. So 47 plus 23, which means it's going to be, it's going to be 70 feet away. It's a possibility. If they're here, it could be 70 feet. But if they're right here, then we do 47 minus the 23 feet away, and we see they're 24. So they could be anywhere from 70 to 20 or 24 to 70 feet away. 24 to 70 feet is the distance they could be from their cell phone. All right, number 4. Each row contains the degree measures of 2 complementary angles. Complete the table. Complementary means they have 90 as the sum. All right, so we can think of this as the equation here. This is going to be 90 minus 80, which is going to be 10 degrees. 90 minus 25, which will be 65 degrees. 90 minus 54, which will be 36 degrees. And 90 minus x is simply 90 minus x. Number 5. Here are 2 patterns made using identical rhombuses. Without using a protractor, determine the value of A and B and explain or show your reasoning. Okay, cool. These are kind of fun here. So we have the A. These angles are all the same, right? All these form a circle. So if I put 1, 2, 3, 4, 5, 6 of these together, so 6 A's is going to be equal to 360 degrees, because that's what I have inside of a circle. So now if we divide the 360 by 6, I find that A has a value of 60 degrees. Okay, so now A is 60. Great, so that's awesome. So does that help me with all the rest of the stuff? Not exactly. It can. I could probably, from here, I could assume I have a supplementary angle, right? Is one way of thinking about that there. And so if that's supplementary, I could do 180 minus 60 and have 120 for B. That's one thing you might see. What else you might see is if I look here at this shape there, okay, I have a 60 over here, a 60 here, and I have a B and a B. So, and again, it's a whole circle, right? So the 60 plus the 60 plus the 2 B's is going to equal the 360. So that's 120 plus 2B equals 360. If I subtract 120 from both sides, 2B equals 042, 240. Divide both sides by 2, and B equals 120 degrees. So we have an angle measurement for B and one for A. Notice that the B matches what? Right there, because why? It's a quadrilateral, and so the sum of those angles is going to be a little bit bigger. All right, anyways, so that's it. Number 6, May's family is traveling in a car at a constant speed of 65 miles per hour. At that speed, how long will it take to go 200 miles? So she's doing 65 miles, right, every hour in 1 hour. That's the rate that she's traveling at. We want to know how long will it take her to travel 200 miles. Okay, so we could set up as a ratio if we chose to. So 65 miles in 1 hour is how many miles, she's going to go 200 miles in how many hours. And so again, this becomes 65 per hour. And how many hours is it going to take to get to be 200 miles? So 65 times how many hours can get me to 200 miles? So we divide both sides by 65, and x is going to be equal to 3.1. Okay? So I just kind of, I already did the math on a side of a piece of paper. So 200 divided by 65 is 3.1. So it's going to take 3.1 hours to get there. How far do they travel in 25 minutes? Okay, well, think of it this way. They do 65 miles in 60 minutes because it was 1 hour. So we want to know how many miles they travel in 25 minutes. So again, that's my proportion there. So 25 times 65 is actually 1,625 divided by 60. And when I do 165 divided by 60 to find out the value of x, I find out that I end up with about 27.08. Is about how many miles they travel in 25 minutes. Okay, that is it for today. We will see you next time.